Hello, so in this video we're going to look through something called confidence intervals. So we are really at the heart of what statistics is all about. You remember like the first few themes we looked at representing data, and we looked at what the point of statistics was. We also looked at like probability. Now really that's less to do with statistics and more kind of background information that you need. It's still important. You need that in order to get into statistics. But right now we are really at the heart of what statistics is about. And if you remember this analogy, I've introduced it a couple of times now. This really signifies what statistics is about. Imagine you've got a cake, okay? Perhaps it's a cake which your grandmother's made, and you want to ask the question, does this cake taste nice? Is this cake delicious? Is it yummy? Okay. Well, clearly you do not have to eat the entire cake in order to answer that question. You can just take a sliver or a slice of cake in order to answer that question. If that slice of cake tastes nice, then that'll be an indication over whether the whole cake tastes nice. So really what we're talking about here is a difference between a population, in this case the entire cake, and a sample, in this case just a slice of that cake. Okay, so population is the entire cake, the entire group of interest. Then you've got the sample, which is just a little subset of that bigger cake, of that bigger population. And the idea is if you can take a sample, because samples are a lot easier to collect than looking at data for the entire population, if you can understand about what's happening at a sample level, then you can make an inference about what's happening at population level. And this is really where at the heart of this. And of course, there's two kind of key terms here. You've got a parameter, which is a measurement of the population. For example, the average weight of a population. And then the measurement of the sample is called a statistic. For example, the average weight of that particular slice of cake. Okay. Then the data, if you like, is the individual ingredients. It's the individual elements that make up the population or the sample. Okay, so this really is a good analogy which I want you to really have in your head about what statistics is all about. It's all about collecting sample data in order to make an inference about what's happening at population level, understanding how sample level data relates to population level data as well. Okay, so what's confidence intervals all about then? Well, let's think about sampling. Okay, I've just established in that last slide and in previous videos as well, statistics is all about making inferences about a population from sample level data. So the idea is you don't have to go out and collect data from the entire population, which is not just very long, it can also be quite expensive to do, and it can also be quite difficult to analyze that amount of data. You don't need to do that though, because you can just select data from a sample, which is like a little subset, and as long as, you know, we've talked about different sampling methods like stratified sampling and first past the post sampling, for example, and convenience sampling. So different types of sampling, as long as that sampling is random. In other words, it gives a good, fair representation of what's happening at a population level. So it's like if you want to go out and find the average weight of fish in a lake. Okay, it don't just mean that you just select fish from one particular corner of a lake. You want to select fish from an entire representative sample. Okay, so you want to select fish from lots of different places within that lake in order to get a fair, balanced picture of what's happening here. Another example of non-random sampling, for example, if you want to work out the average height of people in the college, well, if you just collect together males as your sample, then that's not going to be fair because, of course, there's males and females in the college. Also, same kind of thing with like teachers and students. It'd be poor if you just selected teachers or just selected students. You want to collect a kind of fair, balanced sample of everybody to kind of give a true picture of what would be happening in the population. So random sampling is really important. But the idea is that we've established about making inferences about a population from sample level data. And we've also understood the central limit theorem. We're going to be playing on that a bit more in this video. So that was covered in the last video in more detail. So if you're not familiar with the central limit theorem, please go back and watch that. But the central limit theorem literally tells us how to make an inference about a population from sample level data. And it's really this idea here. We basically saw, and I think we did it with song lyrics, that as we take more and more things in our sample, in other words, our sample size increases, effectively, it should follow a normal distribution. So again, normal distribution, we're relating it back to what we've done in previous weeks. The majority of things should happen in the middle of this data. So the kind of average values, the kind of most representative data, the majority of it should occur somewhere close to the middle. Then you've kind of got outliers each side, so things which lie outside the general trend or the general pattern of your data which is happening. And the idea is, as you consider more and more samples, you get a distribution that looks more and more like this. In other words, there's less variability. The sample mean should approach the true population mean. The spread of the distribution should decrease. And therefore, the probability of obtaining samples or means which are not the true population mean should also decrease as you take more and more samples. So this is really the central limit theorem. And we're going to play on this a little bit more in this video. So I'm going to go back to my song lyrics because I think we understood that in the last example and I think it makes sense to relate it again here. So let's suppose we want to work out the average word length of a song, and in this case I'm using Beyonce's Crazy in Love, and I've got the lyrics over here on the right hand side of the page, okay? So what we could do, because obviously I don't want to go through and calculate every single word, count the number of letters in every single word, then take the average of that big sort of data set. What I'm going to do instead is be slightly quicker, slightly more clever about it, and take a sample. And I'm going to take a sample of 5 words, and I'm going to take the average word length of that sample. Okay, so let's suppose I take the words "oh, crazy, looking, right, and now." Okay, so that's my sample 1. That's what I'm going to call sample 1. And the mean number of letters in that sample of 5 words is going to be 4.6. So I take 2 to be the number of letters in the first word, 5 to be the number of letters in the second word, and so on and so on and so on. Take the averages of the number of letters which I've got here, and it comes out as 4.6. So the average number of letters for my first sample is 4.6. Now obviously I want to increase the accuracy of this because, you know, I look at this and I kind of go, well, okay, how accurate is 4.6 related to the entire population? Well, probably not that accurate at the moment because I need to increase the number of samples, okay? So if I increase the number of samples, I take another 5 words and another 5 words and another 5 words and keep taking the average number of words within each sample, then suddenly I'm building up a new data set. And this new data set is representing the average number of letters in each sample that I'm taking. So I've got 4.6, that's the average number of letters in sample 1. 4.8, that's the average number of letters in sample 2. 3, that's the average number of letters in sample 3, and so on, then 3.4 and 3.6, okay? Now, okay, I did this by hand, so I literally just went through and just literally took 5 words and I did it 5 times, okay? So I took 5 words, took the average, did it again, took 5 words, took the average, did it again, took 5 words, took the average, and did that 5 times, okay? Well, having a look at this, I'm going to then plot this on a normal distribution. So these averages, so the averages of the sample, I'm going to plot these. And you realize that it starts to build up this normal distribution, okay? In other words, most sample means will be roughly the same. They'd be roughly about, well, it looks to be about 3.5, 3.6, somewhere in the region of about 3 to 4, right? But then sort of sample means further away from that range will end up with a lower probability. You're less likely to get sample averages which lie further away from kind of 3 to 4 range, right? Okay, so could I then use these samples? So these samples here, these 5 samples I've taken, and I've taken the average number of words in each sample. Could I use these averages of the samples to kind of give me an indication of what's happening at the true population level? Well, I think yes, I could. However, it comes at a bit of a caveat, okay? I cannot find an exact value. Okay, so in other words, I'm not, from these kind of samples here, I'm not able to look at these samples and say, yep, your true population mean is this. I can't give that. I can't just give one number. So what I'm going to do instead is give a range of values. I'm going to say roughly where the true population lies. I'm going to be like, well, it lies between here or here. Okay, that's my goal. Okay, so I can't, using this, I can't come up with an exact value, but I can come up with a range of values. I can kind of narrow a range down and be like, well, it's about here to here, right? Which I think is good enough, right? So here's the idea. What I'm going to do is I'm going to let X bar represent the means of all of my sample means. So in other words, when I take 4.6, 4.8, 3, 3.3, 4.6, each of these numbers represents the mean number of letters of 5 words. So sample 1, oh crazy, looking right now, take the average number of letters in each of those 5 words, that comes back as 4.6. And then the same with the second sample. So these numbers, 4.6, 4.8, 3, 3.4, 3.6, when I plot them on a curve, I get this. And what I'm going to do is then take the averages of the averages, if you like. So these numbers which are already averages, I'm just going to take the averages of those, okay, to increase my kind of accuracy, okay? So here I'm going to put X bar in the middle, which remember represents the average of each of those samples, the average of those 5 sample means, okay? And then what I'm going to basically say is, look, my true population mean weight, word length in this case, is going to lie between this value and this value. So I'm going to say, well, look, here's x bar, and I'm just going to basically add on some particular value and then take away some particular value. So I'm basically saying that the true mean word length should lie somewhere between this range, okay? I don't know where exactly it is, but I can kind of narrow it down that it's going to lie somewhere between this range. This is my idea, okay? Now, clearly it's an interval or a range of values, and you can kind of see here that why we call it a confidence interval, because I'm literally giving an interval, a range in which that true population mean can lie, okay? So here's how I could write this as an inequality, okay? Because I've got x bar in the middle and I'm basically adding on some margin of error and taking away some margin of error. In this case, I'm just calling the margin of error m, okay? Then I basically say, well, written as some inequality, the true population mean should lie between x bar minus that margin of error, so that's my lower bound, up to x bar plus some margin of error, so that's my upper bound, okay? So here's the idea, okay? I can, using this 4.6, 4.8, 3, 3.4, 3.6, I can calculate the average of those averages and the standard deviation of those averages, okay? So how can I calculate the mean? Well, quite simply, just add them all together and divide by the 5 samples I get. And I get my average of my averages as 3.9, which you can see lies roughly in the middle of these sample means when I plot them on a standard deviation curve, normal distribution curve, okay? I can also take the standard deviation, okay? So standard deviation is just simply the average distance from the mean. So now I've got the mean as 3.9, I look at 4.6 and 3.9, look at the difference, and then square it, and so on and so on and so on, okay? And then clearly, because it's a sample, I'm going to do 5 divided by 1 on the, 5 minus 1 on the denominator, which is my degrees of freedom, because I'm looking at a sample here, not the entire population. So I'm going to divide by 4 instead of 5, because I'm doing a sampling correction there. Okay, so in other words, I get my standard deviation as 0.8, and I know that a normal distribution should have the true mean roughly in the middle, and then basically one standard deviation each side, and we looked at the probabilities of obtaining values within each of those regions. Okay, so this is kind of standard normal distribution stuff at the moment. Okay, so in other words, what I can do is look at the proportion of data which lies within each of these regions. Okay, so in other words, if I've got the mean value in the middle, the probability of obtaining a value between the mean value and one standard deviation above or below that mean value should be 34%. Okay, so one standard deviation below the mean should be 34%, one standard deviation above the mean should be 34%. So in other words, I literally know how much of my data I should expect to lie within each of these regions if I look in units of standard deviation. Okay, so this is just normal distribution, what we were doing a couple of videos ago. So in other words then, our sampling distributions, just to kind of recap, what we've got is a sampling distribution. We've gone out and we've selected samples of 5 words, and we've just simply taken the average of those samples, okay? And I know that if we do that enough times, it should follow a normal distribution. That's literally what the central limit theorem tells us, okay? And I know what the features of a normal distribution should be. In other words, the true population mean should lie somewhere in the middle, and then basically I can look at one unit of standard deviation each side, and I can look at the proportion of our data which should lie in each region, okay? So therefore we're looking at an interval for our true population mean from our samples, okay? And I can use these proportions, I can use these areas underneath my normal distribution to work out how much data I should expect to lie in each of these regions, okay? So here's the idea, okay? I know that my true population mean should lie somewhere between here and here. So I need to decide how confident I want to be that our interval that we come up with contains the true population mean. Because are you happy that if I use I want to be 100% confident, or nearly 100% confident at least, then I know that I need to be looking about 3 standard deviations each side of the mean, okay? Because 3.5 standard deviations each side of the mean contains nearly 100% of our data, okay? That's one of the features of the normal distribution. We said that anything beyond about 3.5 standard deviations each side of the mean has such a low probability of occurring that we can basically say that the majority of our data, nearly all of our data, nearly 100% of our data occurs between 3.5 standard deviations each side of the mean. Okay, so in other words, if I want to be 100% certain that I've actually captured that true population mean, then I need to look at 3 standard deviations each side of the mean. Okay, however, it means that our interval is going to be very large because I'm containing huge amounts of values. I'm basically saying, well, look, the average number of word lengths, okay, it's between like 0 and 100. Well, that's rubbish, right? That's such a big interval that I could have done that without doing any kind of sampling at all. I could just eyeballed it and be like, it's been between about, I don't know, 0 and 100, okay? Or obviously it's going to be a little bit narrower than that. But my point is, if you want to be nearly 100% certain, you get a very wide interval, which is not really what you want, okay? So in order to narrow the interval down, what I can say is, look, only look at one standard deviation each side of the mean. So instead of looking at 3 standard deviations each side of the mean, which we're doing there, and ending up with a very large interval, but I was very confident that the mean value lies between those values, okay? Let's narrow it down. Let's only look at one standard deviation. Well, the trouble is, if I only look at one standard deviation each side of the mean, then are you happy that I'm only looking at 68% of our data? Which means that I can say, well, look, the average word length for our song is between 3.1 and 4.7 letters. That's better. I've narrowed the interval down, but I'm only 68% confident in that. Okay, because I'm only including 68% of my data, which means that 32% of my data won't be included, and there is a 32% chance then that my true population mean actually lies in the regions which I haven't included, okay? So my point is that there's a little bit of a trade-off, okay? It's a trade-off between confidence and specificity. So in other words, I could be really confident. I could say, yeah, I'm 100% confident. But as a result, my confidence interval is very, very wide. In other words, I'm saying that my true population mean is lying between like, I don't know, like 1 and 10, right? It's a really wide interval. It's not very narrow. It's not very specific, okay? Now I could increase my I could decrease my my interval and say, well, look, my mean number of word, or my mean word length rather, lies between, say, I don't know, 3 and 3.7. But as a result, I'm going to be less confident, because I'm making that interval smaller, which means I'm rejecting the outlier values. I'm rejecting more values. So it's really a trade-off between confidence and specificity. The more confident you are in your confidence interval, the more confident you are that you've actually captured that true population mean, well, you've got a larger interval as a result. So you're basically not being very specific. You know, it lies between 0 and 10. My average number of words, my mean word length lies between 0 and 10. Yeah, I'm very confident in that, but it's a very wide interval. But in order to be more specific, my confidence level goes down because I'm rejecting more values. Okay, so hopefully that makes sense. So in other words, how do I actually go about calculating something like this? Well, I need to work out what my margin of error is. So remember that M literally defines the size of the confidence interval. It's how wide my confidence interval is. So therefore, I need it to depend on the units of standard deviation. Okay, so let's say, for example, I want to be 68% confident. I want my confidence level, how confident I want to be that my interval contains the true population mean word length. If I want that to be 68%, then I'm going to be looking 1 unit of standard deviation each side of the mean, okay? Because that's 34%. You can see that region highlighted there, okay? So in other words, my value of M will be, well, 1 unit of standard deviation times by whatever my standard deviation value is, because I need to be including 1 unit of standard deviation each side of the mean in order to include 68% of my data. If I want to be 95% confident, then I'm basically going to be looking at 2 units, roughly 2 at least, 2 units each side of the mean, so 2 units of standard deviation. So therefore, M is going to be given by 2, which is the number of standard deviations, times by whatever my standard deviation value is. If I want to be 99.7% confident that I've contained the true population mean, so very, very confident, but as a result my interval is much wider, then I'm going to be looking at more units of standard deviation, in this case 3, times by whatever my standard deviation value is. So basically the value of M kind of defines on these 3 things. Number 1, I need to find a suitable confidence level. I need to say, well, look, this is a confidence level I'm happy with. And bearing in mind the confidence level and specificity, it's kind of a trade-off. The more confident you are, the wider your confidence level, okay, the wider your confidence interval, which means you're containing more values. Whereas the less confident you are, then the smaller your confidence interval is going to be, okay? So I need to basically find how many units of standard deviation are needed for that confidence interval. For example, if I'm 99.7% confident, I'm going to be including 3 units of standard deviation each side of the mean. So I'm very confident, but as a result, my confidence interval is very wide because I'm including a lot of data in my confidence interval. Okay, and then in order to work out what the value of m is, well, I basically say, well, look, this is how many units of standard deviation I need in order to include that much data. Then I need to multiply that by whatever my value of standard deviation is. Okay, so in other words, I get something that looks like this. Now, you notice the difference between these two things. Strictly speaking, we should be using the bottom one now. Okay, so Z star times my confidence level, that just simply means the units of standard deviation. I find that from my table. So in other words, if I want to be 95% confident, I need to include 95% of my data, which means that I need to work out how many units of standard deviation each side of the mean will include that 95% confidence level. Okay, so 95% of my data. Then I need to multiply that with my standard deviation or my standard error. Now, you notice that I've included the standard error here. So the difference between standard deviation, that's if you just got one sample. You can easily calculate the standard deviation there. Whereas if you're doing the central limit theorem, in other words, you're including more and more samples and you're taking the mean of those samples, for example, then that's going to be the standard error. You just basically need to divide by n. The reason being, by the central limit theorem, that we've noticed is by the central limit theorem that the distribution becomes more peaked as you include more and more data. In other words, the spread of your distribution decreases. So the variance decreases by a factor of n, or the standard deviation decreases by a factor of root n. Okay, and we proved that in the last video. Okay, so this is how you calculate what m is, and then you just simply add and subtract it from your mean, your sample mean, and that's how you find a confidence interval for your true population mean. Okay. So let's actually see this with an example. Let's go back to our SON lyrics. We basically said, well, look, we've collected 5 samples, okay, 5 samples, and we found the mean of those samples, so the mean of the means is 3.9, and the standard deviation of those samples was 0.8. So in other words, I get a distribution that looks like this, or a sampling distribution that looks like this. So each one of these represents the average number of word lengths in each sample, and then the 3.99 represents the averages of each of these 5 averages, okay? And that's in the middle, and then basically I'm just moving 1 unit of standard deviation each side of that mean, so 0.8 each side of that mean, okay? Now, let's suppose I want to do a 95% confidence interval. Now, nearly always, if you're answering questions, they will tell you what the confidence level is going to be. Okay, so how confident you want to be that you've actually contained the true population mean. However, if it's not, a good one to go for is 95%, okay, because that allows it to be small enough that you're being fairly specific. So it's not like 100% or 99%, which is going to be a really wide confidence interval. Okay, 95% is going to be small enough that you can be fairly specific, but it's not so small that you've kind of lost all confidence in your confidence interval. Okay, so let's suppose 95% is a good one to go for. Okay, so what I'm going to do is I'm going to first of all ask the question, how many units of standard deviation each side of the mean, each side of my sample mean, will include 95% of my data? So here's my sampling distribution. How many units of standard deviation do I need to look at each side of 3.9 in order to include 95% of my data? Well, look, I basically want the area underneath this curve to be 95%. So I need to look some units of standard deviation that way, some units of standard deviation that way. It's symmetric, so I expect it to be the same units of standard deviation each side. And I basically want that to be 95%. Well, okay, if that area is 95%, if I want to then apply this to the tables to find the units of standard deviation, I know the leftover bit is 5%. And that's split amongst 2 regions. There's a region here, there's a region here, it's symmetric. So in other words, each region is worth 2.5%. So in other words, to find the appropriate probability, I just need to find 2.5% in my tables and then find how many units of standard deviation correspond to 2.5%, okay? So if I do that, I'm basically saying, well, what's the probability that Z is less than some value is giving me 2.5%? Well, then I find that that value is about 2 units of standard deviation, okay? So because I'm looking at 2 units of standard deviation, and that will include 95% of my data, then I just basically say, well, look, 2 units of standard deviation. What is my standard deviation? It's 0.8. So in other words, my margin of error is going to be 2 lots of standard deviation. In other words, it's going to be 1.6, 2 times 0.8. Okay. So therefore, to construct my confidence interval, I'm going to say that my true population mean is going to lie between, well, x bar minus this margin of error, this 1.6, to x bar plus that 1.6, that margin of error. So in other words, my x bar, I've got it up here, is 3.9. That's my sample mean. Okay, that's my 3.9. If I take away my margin of error, which is 1.6, and then my upper value is 3.9 plus 1.6, then I end up with a confidence interval of 2.3 to 5.5. In other words, what this is literally saying is that the true population mean, so the true population sort of average number of word lengths, will lie somewhere between 2.3 and 5.5, okay? And I can be 95% confident that that is correct. So I can be 95% confident that my true population mean lies between 2.3 and 5.5. Okay, so the true population average number of average word length lies between 2.3 letters and 5.5 letters. Now clearly, I could make this interval more specific, but if I make it more specific, in other words smaller, I'm also decreasing my confidence level because I'm rejecting more data. Okay, I'm only looking at smaller regions of data. So just be aware of that. Okay, so we're going to be 95% confident the true population mean word length for the entire song lies between 2.3 and 5.5 letters. Okay, now I want to just play on this idea of the confidence level a little bit more. How do we actually interpret it? What does a 90% confidence interval actually mean? Okay, well, it literally means that, well, what we're doing here is we're constructing confidence intervals from samples. In other words, we're going out, we're collecting a sample. In this case, we're collecting samples of 5 words from our song, and we're doing that multiple times. And then for each of the samples that we take, we can construct a confidence interval for each of them. Okay, so in other words, what 90% confidence level literally means is that 90% of all of the confidence intervals that we construct, okay, 90% of all of the samples that we take will contain the true population mean, whereas 10% won't. They won't contain the true population mean. So that's how to interpret the 90% confidence interval. A 95% confidence interval would mean 95% of all of the confidence intervals you construct of your samples will contain the true population mean. 5% won't if it's 95% confidence level. Okay? If you want to be a 50% confidence level, that basically means that 50% do contain the true population mean, 50% don't. Okay? So if you actually want to visualize this with a 90% confidence interval, let's suppose that this is a number line, and I basically plotted the true population mean word length on my number line here. Okay? Now what I can do is basically take loads and loads of confidence intervals. So I can take loads of samples and construct a confidence interval for each sample. Okay, so let's just take 10 just because it's convenient. I've got 90% here. Then what that means is that 90% of all the confidence intervals that I'm going to construct will contain the true population mean, but 10% of them, in other words 1, won't. Okay, so if I just look at this first one, well, okay, this is my first confidence interval for my first sample. Okay, that contains a true population mean. You can see it ends up here. Remember, all I'm looking for is that the true population mean occurs somewhere within this interval. Okay, I don't care where it is, just happens to have somewhere. That's all a confidence interval tells you. Okay, so in this case, yep, the true population mean does lie within that interval. If I look at sample 2, well, that doesn't. Okay, it completely misses the true population mean. But if you have a look, all of the other 9 do actually contain the true population mean. So what does 90% confidence interval literally means? Literally means that 90% of all of the confidence intervals that we construct will contain the true population mean, but 10% won't. Okay, so again, it's this kind of trade-off. Sure, you can be 100% confident, but that would just mean that you end up with a really wide confidence level. So again, it's confidence level versus specificity. Okay, so just be aware of that. Okay, so again, just coming back to the central limit theorem then, just do you remember what the central limit theorem says? I'm sure you could kind of recite this well enough by now because we've gone through it enough times. But we said that as the sample size increases, we get a normal curve that is effectively more peaked. What that basically means is it's less spread out and it's more centered around the true population mean. So you can see over here that the curve in green represents a small sample size. It gets flatter, more spread out. But then as I consider more and more things in my sample, in other words, a large sample size, it's much more peaked. In other words, there's less variability, there's less spread, okay? So therefore, if there's enough samples in my, if there's a large enough sample size, I can use a Z-curve, okay? In other words, I can use the standard normal distribution. Remember, Z is the Z-curve which has a mean of 0 and a standard deviation or variance of 1, okay? So if the sample size is large enough, I'm fine to use a Z-curve. I'm fine to use a standard normal distribution. However, we've seen that if there's a smaller sample size, it's not fair to use my Z-curve. It's not fair to use my standard normal distribution because actually I expect it to be slightly flatter, more spread out than my standard normal distribution, okay? Because it's less peaked. So what I'm going to do is I'm going to have to come up with another curve because the Z curve isn't accurate enough. Well, yes, at least, because its sample size isn't big enough. It's not peaked enough to be the true standard normal curve. Okay, in other words, the true probabilities on this curve should be lower. Okay, so what I'm going to do instead is I'm going to use a sampling distribution or a T curve. Okay, so the T distribution instead. So in other words, if I have a large enough sample, I'm fine to use the Z curve. I'm fine to use the standard normal distribution. However, using the central limit theorem, we can see that for smaller sample sizes, this curve is effectively more spread out. In other words, I'm going to have to use a slightly sort of different correction, and we do that using a T curve, and the T curve basically just corrects for it. It follows exactly the same kind of shape, it follows that same sort of bell shape as a Z curve. There's nothing really different about a T curve, apart from the fact it's more spread out. So it's a kind of compensation, okay? If the sample size is big enough, fine, just use the Z curve, use the standard normal curve. However, if the sample size is too small, then it's going to be a flatter curve. So to compensate for that, we're just going to use a slightly different curve. It has the same kind of shape, it's just slightly flatter, and this is where the T curve comes in. Okay, so let's have a look at this. We've just said that the T curve follows exactly the same shape as the Z curve, okay? But it'll be flatter and less peaked, which means that the probabilities will be lower. Okay. Now, to indicate the sample size, because clearly we've seen with the central limit theorem that as the sample size increases, this curve has to become more peaked. And indeed, the T curve does become more peaked as you consider different sample sizes. To indicate that, we use something called the degrees of freedom, or Bessel's correction. And that's just basically the number of samples take away 1. Okay, so n minus 1 there. So sample size is always given by n minus 1. That's the degrees of freedom. Okay. And we've met that before in the first sort of video when we were looking at standard deviation. You remember that the formula for standard deviation varied against whether you're using the sample standard deviation or the population standard deviation. Okay, population standard deviation, just divide by n, it's just the average of all of the distances you've got. Whereas if you're looking at the sample standard deviation, you need to divide by n minus 1, and we looked at that in that first video. Well, here we go again. Degrees of freedom again comes in here because it's simply saying, well, look, I want to indicate sample size, and the sampling correction is always just n minus 1. It's the degrees of freedom. If you want a little bit more information about what degrees of freedom literally says, it's literally the amount of things that are allowed to change before you know everything in your data. So just a very quick example, it's the number of things that are allowed to change before you know everything about your system. So as a very quick illustration, let's suppose we've got this situation here. So basically, it's a very crude drawing. Each of these are cups. So I've got a cup here, and a cup here. Okay, and they're sitting on a surface upside down. So sitting on a surface upside down. And of course, they're completely opaque, so you can't see through. But basically what I've done is I've placed 2 balls underneath 2 of the cups. Okay, and you can see which cups I've put them under here. Well, clearly, all I have to do, so degrees of freedom is literally saying, how many things do I have to know in order to know everything? So in this case, I need to know what is under 2 of the cups, okay? So for example, let's suppose I look underneath this cup here, and I see there's a ball, okay? So I see there's a ball there. So I know that there's a ball there, but I know that there has to be 2 balls in the system. Okay, so do I know everything about the system? Well, no, I don't, because are you happy that if I just looked at this, there wasn't any, I couldn't see the cups. The ball could still lie in either cup, okay? So therefore, I need to know at least one other thing here, okay? So let's suppose I look under here and I find the ball, okay? So the ball is under here. Now I know everything about the system, okay? I know the ball is under the first cup and the second cup, and it's not under the third cup. So in other words, as long as I know what lies under 2 of the cups, I know what has to lie underneath the third. That's what I mean by degrees of freedom. It's the amount of things that are allowed to change. It's the maximum number of things which are allowed to change before I know everything about the system. Okay, so in this case, I'm basically saying, as long as I know what's underneath 2 of the cups, there's 3 cups in total, as long as I know what's underneath 2 of the cups, in other words, n minus 1, number of cups minus 1, then I know everything I need to about the system. Okay, nothing else in the system is allowed to change as long as I know 2 of the things. Okay, so that's a really important feature. So that's degrees of freedom, and that's how we indicate the sample sizes. Okay, it is important to say as well that, strictly speaking, we should always use a T curve. Okay, but the thing is, as we get large enough sample sizes, the t-curve and the z-curve is just exactly the same anyway. So actually we say that as we increase the number of samples, because it becomes more peaked, the t-curve approaches the z-curve anyway, so eventually you're fine to use a z-curve, okay? And we basically say that for any sample size over 30, in fact we say 30 or over, the z-curve and the t-curve will be indistinguishable, therefore it's fine just to use the z-curve as long as it's greater than or equal to 30, okay? So as long as n approaches infinity, the t-curve will approach the z-curve, and we basically say that for anything, any sample size which is greater than or equal to 30, the t-curve and the z-curve, they're exactly the same. So to be honest with you, if a sample size is greater than or equal to 30, you're fine to use the z-curve. But if it's less than 30, you must use the t-curve because there's going to be a slightly flatter curve there, okay? So I always use this little sort of check to see which curve I need to use here. So first things first, is my sample size bigger than or equal to 30? Okay. If the answer to that question is no, then I must use the t-distribution. Okay, so basically, if I have a small sample, n is less than 30, then I have to use this t-distribution. If the answer to that question is yes, then there's something else I need to consider. Because you remember this whole idea of the t-curve and the z-curve, the t-curve is more spread out, okay? So in other words, there's a measure of spread going on here. So in other words, I need to ask myself, well actually, do I know what the true population standard deviation is? So in other words, do I know sigma? Do I know sigma? Do I know the true population standard deviation? If the answer to that question is still no, then actually I would use the t-distribution just to be safe. So even if we have a large enough sample size, that n is greater than or equal to 30, always ask yourself the question, well actually, do I know what the true spread of my distribution should be? If the answer to that question is no, then use the t-distribution just to be on the safe side. If the answer to that question is yes, then you're fine to use the z-distribution. So in other words, what I would sort of take away from this is ask yourself two questions. Is the sample size big enough? Is n greater than or equal to 30? By the way, we just use 30 because that's the point where the t-curve and the z-curve is kind of indistinguishable. It's pretty much the same thing, okay? So is my sample size bigger than or equal to 30? Second question I need to ask myself, do I know my true population standard deviation? If the answer to either of those questions is no, use the t-distribution. Whereas if the answer to those questions is yes, so they need to both be yes, then I use the z-distribution. So you could always just say, instead of using this tree, do I have a big enough sample size? Is n greater than or equal to 30? And do I know the true population standard deviation? Do I know sigma? If the answer to both those questions is yes, use the z-distribution, otherwise use the t-distribution. Okay, so just remember this little table, this little decision tree here. Okay, it is also important to remember that the t-distribution has a measure called degrees of freedom, okay? And degrees of freedom is there to indicate the sample size. It helps to kind of establish how spread out that curve is, okay? Because that's again indicated by the sample size, by the central limit theorem. So therefore it should be n minus 1 is the degrees of freedom. Okay, so let's have a look at this question here. So we've been told that the weights of chocolate bars are known to be normally distributed with a standard deviation of 3 grams. So I'm going to actually box that, that's my standard deviation. Now you notice the way that the question is worded, that 3 grams is saying, well look, the weights of chocolate bars are known to be normally distributed with a standard deviation of 3 grams. The way that that's implied, that's our population standard deviation, that's sigma. Okay, so we didn't actually collect a sample and calculated that. That's kind of given to us in the question. Okay, so therefore we can assume that is the true population standard deviation. We then go on and told that a sample of 20 chocolate bars, okay, so 20 chocolate bars, is collected and found to have a mean of 100 grams. In other words, that's my sample mean. Okay, so this here is my sample size, n is 20, and here is my population, or my sample mean. Okay, that's my x bar. Construct a 90% confidence interval, so that's my confidence level, and I'm going to call that CL for short, for the population mean weight. So first things first, I need to figure out, okay, well I need to construct a confidence interval. Do I need to use a z-curve or a t-curve in order to do this? Well, okay, let's just ask ourselves the two questions I need first of all. So first things first, what's n? Is it greater than or equal to 30? Second question, do I know sigma? Okay, so those are the two questions I ask myself. If the answer to the first question is yes, then I need to ask that question. If the answer to the second question is yes, then I can use the t-distribution. Whereas if the answer to either of these questions is no, then I have to use the t-distribution. So sorry, my mistake. If the answer to both those questions is yes, I need to use the z-distribution. Okay, so just also always ask yourself those two questions. Is n greater than or equal to 30? Is sigma known? If the answer to both those questions is yes, use the z-distribution. If the answer to either of those questions is no, then use the t-distribution instead. So here we go, let's go up here. Well look, I've got sigma is equal to 3, so let's actually write this down. So let's write our data down. So we've got sigma equals 3, n is equal to 20, and our x bar, our sample mean, is equal to 100. Okay, and our confidence level, so I'll write CL for short, is 90%. Okay, so let's have a look at this. Okay, so these are the questions that we need to ask. So basically I'm boiling that question down to this summary statistics over here. Okay, well let's have a look. Is n greater than or equal to 30? Well no, it's not. N in this case is equal to 20. So because the answer to that question is no, I know immediately I need to be using the t-distribution. Okay, even though I know my population standard deviation, it doesn't matter because the answer to the first question is no. Do I know n is greater than or equal to 30? One of those questions is no, then I must have to use the t-distribution instead. Okay, so let's do this. So basically I'm going to construct a confidence interval for my mean. So in other words, I'm saying that my true population mean, that's mu, is going to lie within some margin of error of my sample mean. Okay, and I just need to work out what that margin of error is going to be. Well, just remember the way which I work out my margin of error is first of all the number of standard deviations. Okay, so I need to look up my t-distribution now because it's t star, so I write my t value because I'm using a t-distribution of my confidence level. So in this case my confidence level is 90%. So I need to look up, well okay, how many standard deviations am I going to look at if I want to include 90% of my data underneath my curve? Then I need to multiply that. Well, I need to multiply it by my standard error because in this case, I'm selecting a sample of 20 objects. So in other words, I'm saying that if x is my mean weight, okay, so x is the mean weight, weight of my chocolate bar, isn't it? So my weight of my chocolate bar. Then when I take multiple chocolate bars, in this case 20 chocolate bars, and put them all together, I get a new distribution, so x bar is my new distribution, still normally distributed, okay? But in this case, the mean weight is still going to stay the same. It's still going to stay as 100, but the standard deviation, which is 3, and the variance, which is 3 squared, is going to decrease by a factor of n. So in this case, it's going to decrease by a factor of 20, okay? So there we go. So that's my new distribution that I need to work with. Okay, so in other words, my standard deviation, or my standard error in this case, because I'm looking at multiple samples instead of just one, is going to be 3 divided by the root of 20. Okay, so that's actually my value of my standard deviation, standard error, and that's how many standard deviations I need to be looking at, okay, in order to include 90% of my data underneath my sampling distribution. Okay, fantastic. So let's actually work this out then. So first of all, I'm going to work out how many standard deviations I need. Well, in order to do that, I need to know what my degrees of freedom are because I'm looking at t-distribution. So here we go. So if I got n is 20, that means that my degrees of freedom must be 19. It's always one less than whatever sample size I'm looking at. Okay, so in this case it's 19. So then I can bring up my my tables. Okay, so if I bring up my tables, so here are my t tables. Oops, let's make sure they bring them up. There we go, there's my t-tables. Now the way which they work is very similar to our normal tables. We've seen the normal tables before. So these are the t-tables, okay? And it basically says, well, okay, what's the probability of obtaining up here? Or of course, if I wanted to put in t star negative, because of course it's symmetric, it's basically what's the probability of lying down here as well, okay? So the way which it works, first of all, you see this first kind of column. This is basically our degrees of freedom. This is going to dictate which row we're going to be looking at. Well, in this case, our degrees of freedom is 19. So therefore, I need to be looking at the row which has 19 in them. So let's zoom in slightly. So if I find the row which has 19, there we go. So I'm going to be looking at this row here. Okay. Then which column do I need to look at? Well, there's two ways of doing it. Number one, you look up here, you see it's the upper tail probability. What that basically means is that when I draw myself out my curve, okay, so when I draw my curve out for this situation here, so I get my t curve, which remember looks exactly the same as my z curve. I mean, it follows the same kind of principle, so kind of in the middle, I've got my average, okay? Then I'm basically saying, okay, how many standard deviations each side of the mean do I need to look at? So plus m and minus m. How many standard deviations each side? Well, look, I want the area, I want to include in this case 90% of my data because that's my confidence level. My confidence level is 90%, which means I want to consider 90% of my data, okay? Which then means that my upper tail probabilities, well, look, I've got 10% left over because the area underneath my entire curve should be 100%. So the area I want, the one shaded in red, is 90%. The leftover area should obviously be 10%, but that's split among two regions. There's a region here and there's a region here, which means each region is going to be 5%. Okay, so in this case, my tail probabilities is 5%. So when I come to my tables here, I'm going to be looking at my tail probabilities as 5%. In other words, that value there. Okay, and if I scroll down, I basically find that is the value I'm after. So 1.729 units of standard deviation each side of the mean. Okay, so that's my value there. So 1.729 units of standard deviation will give me 90% of my data on this curve. Now you also scroll down, you notice there is also another measure which I could use, which is the confidence level. So I could either use the probability, the tail probabilities, which is what I just did, or I could use the confidence level. Well, in this case, my confidence level is obviously 90%, which still means that I'm going to be using that particular column. So either way you do it, doesn't matter which way you do it, I don't care. Okay, either way you do it, either using your confidence level, so down the bottom, or using your tail probabilities, it's still going to give you the same kind of thing. So it's still going to give you 1.729. Okay, so there we go. So there's our 1.729. I need to multiply that by our value of our standard deviation. So let's actually stick all of that into our calculator. I'm just going to stick it on a calculator just for time rather than bring the calculator up. So 1.729 times by our 3 over the square root of 20. That's going to give us 1.16. Okay, so basically our margin of error is 1.16, in this case grams, each side of our sample mean. Okay, so in other words, when I come to actually calculate my my confidence interval, I'm saying that my true population mean, remember, has to lie between x bar minus some margin of error and x bar plus some margin of error. Well, in this case, our x bar, let's find it, our x bar is equal to 100, okay? So our x bar is equal to 100. Our margin of error, we've just calculated that, is 1.16. So our lower value is 100 take away 1.16. Our upper value is going to be our x bar, which is 100, but this time plus our margin of error, so plus our 1.16, okay? So in other words, mu has to lie between, well, okay, 100 take away 1.16 is going to give us our 98.84. Our upper value is 100 plus 1.16, that's 101.16, okay? So in other words, what we can say is that we are 90% confident that based on this sample data that we've collected, so this sample data up here that we've collected here, okay, so standard deviation of 3, sample size of 20, x bar equals 100, we can be 90% confident that the true population mean, so I'll just write M, so the true population, in this case mean weight, lies between 98.84 grams and 101.16 grams. So basically, if we knew nothing else, if we just knew that this is our sample data, this is how many things we've collected, we can still calculate a confidence interval. We can say that 90% of the time, we should expect a true population mean weight lying between 98.84 and 101.16. We're 90% confident that the true population mean weight of our chocolate bars is between about 98, 99 grams and about 101 grams, okay? So that's how we construct a confidence interval. And obviously, if I increase my confidence interval, I'd also increase my confidence level. So I'd be more confident that I'd actually capture the true population mean. If I wanted to be more specific, I could absolutely decrease that population. I could absolutely decrease that confidence level. But as a result, I would be less confident in my sort of interval that I give. Okay, so hopefully that makes sense. Okay. Now, what happens then if we want to change this slightly? Because confidence intervals don't just have to be used to look at one sample or one group. Let's suppose now we want to actually look at two different groups. So let's suppose it might be comparing two different types of batteries, okay? Or scores of two different classes, okay, on a test or something. So then what we could do is look at two different groups, collect data for each of them. So let's suppose we've got standard sample size of N1 for group 1, sample mean of X bar 1 for group 1, and a standard deviation of sample of S1. And the same thing for group 2, except changing it to N2, X bar 2, and S2. Then what we basically are saying is, well, okay, if we collect together all of these samples, okay, all of these individual samples, we get a new distribution down here and a new distribution down here. So I want to work out what's the difference in the mean. So I want to work out, is there any difference between them? Then the day statistics is all about variability. It's all about differences between things. So let's look at the difference between group 1 and group 2. So in other words, I want to work out what the parameters of the distribution of X bar 1 take away X bar 2 would be. What's the difference in these two groups? Okay. Well, in order to do so, I need to basically say, well, look, the value that goes here in the first parameter is our expectation. So what's the expectation of the difference in my mean, of the means of my groups? And the value goes here is obviously the variance. So what's the variance in the difference of my two groups? So let's work out what expectation of this is and what variance this is. Well, good news is it's very, very simple, okay? It's just using expectation algebra. So look, expectation of X bar 1 take away X bar 2. Well, I know that it's exactly the same as expectation of X bar 1 plus the expectation of negative X bar 2. The reason being is because X bar 1 take away X bar 2 is just going to be X bar 1 plus negative X bar 2. So taking away is the same as adding negative, okay? That's all I've done there. And I know that the expectation of two random variables added to each other should just be equal to the expectation of each individual random variable summated, so added. Well, have a look. Are you happy that here I've got the expectation of negative X bar 2? Well, okay, the expectation of some constant, because that's all the negative is, just negative 1, the expectation of some constant times our random variable should be the constant times the expectation of our random variable. That's just expectation of algebra. The expectation of A times Z, for example, should be the A times the expectation of Z. Well, have a look. Plus a negative, that just becomes a take away. So the expectation of X bar 1 take away X bar 2 is just the expectation of X bar 1 take away the expectation of X bar 2. Well, the expectation of X bar 1, we've got that in our formula up here, it's just mu1, okay? And again, expectation of X bar 2, we've got that up here, it's just mu2. So therefore, the expectation of X bar 1 take away X bar 2, the parameter that goes here is just mu1 take away mu2. What about our variance then? Well, okay, what's the variance of this? Similar kind of trick. I can treat that as the variance of that random variable plus the variance of that random variable there. So again, minus just means plus a negative. Of course, I'm assuming implicitly that the two groups are independent of each other. I think that's a safe assumption to make, okay? Otherwise, I'd have to consider covariance and stuff like that. But just for the sake of simplicity, let's just assume they're independent. I don't have to worry about covariance here. Well, okay, if I pull the negative 1 out again, just remember the variance of some constant times my random variable should be the constant squared times the variance of the random variable. The reason being is because, sure, the standard deviation will increase by that many scale factors, okay? But the variance is the square of the standard deviation, which means that constant should also be squared as well. Well, okay, what's negative 1 squared? Well, it's just a positive, okay? So in other words, I'm saying the variance of the difference between these two random variables is the same as the summation of the variance of these random variables. Now, I know the variance of X bar 1, okay? It's just sigma 1 squared over N1. And I know the variance of X bar 2, it's just sigma 2 squared over N2. So therefore, when I put that back, I find the second parameter which goes here should be sigma 1 squared over N1 plus sigma 2 squared over N2. Now that's weird, right? Because this makes sense, okay? The expectation of the differences of my two random variables should be the differences of my means, that makes sense. But the variance, because I'm taking away, it still remains a plus down here. The reason being is when I pull that negative 1 out, I'm putting out negative 1 squared, okay? So in other words, this distribution basically becomes this, okay? It looks very big and difficult and complicated to follow, but it's honestly not. It's just basically taking, look, here's my individual distributions. If I combine them together to make a difference, then I get this distribution instead, okay? So what decision tree should I use? Because now I obviously have two different groups. So now instead of just checking is n greater than or equal to 30, I need to check whether both are greater than or equal to 30. So the sample size of group 1 and the sample size of group 2, I need to check both of them. Check they're both greater than or equal to 30. Okay? If the answer to that question is no, in other words, they're not both, it might be that one is greater than or equal to 30, but they have to both be greater than or equal to 30. Okay, that's really important. If the answer to that question is no, then I use the t-distribution. If the answer to that question is yes, then I need to then go on and say, well, look, do I know the population standard deviations for both of them? And I need to know them for both. Just because I know the population standard deviation for sample 1, for example, if I don't know the population standard deviation for group 2, I have to answer this question as no. Okay, so I need to know standard deviation, population standard deviation for both. Okay. So if I don't know that, then I use a t-distribution. If I do know that, then I use a z-distribution. So effectively, it's the same kind of thing as what you were looking at before when we're just looking at one group, okay? The difference is now is that I need to include both of them, okay? And I need both of these statements to hold. So I need N1 and N2 being greater than or equal to 30. And I need population standard deviation for both group 1 and group 2, okay? If the answer to that question is no for either of them, it's a t-distribution. Otherwise, you can use a z-distribution. Now, what would the degrees of freedom of your t-distribution be? Well, we've just seen on the last slide that you should add the variances together. So you effectively just add together the degrees of freedom for each of these distributions. In other words, the degrees of freedom will be the first group's degrees of freedom, which is n1 take away 1, and the second group's degrees of freedom, which would be n2 take away 1. You just add them together. So that's degrees of freedom for the first group, degrees of freedom for the second group, add them together. Of course, you can use a little bit of algebra there to say n1 plus n2 take away 2 in total. Okay, so that's how you calculate the degrees of freedom. Okay, so let's go through an example then of a difference in the means. So I've not actually written it out kind of wordy. Of course, if you're greeted with this question in an exam style situation or perhaps in a homework, it'll be much more wordy than this. But effectively, let's just talk through it. Let's suppose we're comparing two different batteries, so battery A and battery B. And we go out and we collect samples of each of these two different types of batteries. So battery A, we collect 40 batteries of that sample. We find that the average lifetime or the average duration of those 40 batteries comes back as 200 hours. And the population standard deviation, let's suppose we know that, suppose it's quoted like on the back of the battery or something, to be 5 hours, okay? And for battery B, well, this time we go out, we can only get our hands on 25 batteries in this case. We find that the mean duration for those 25 batteries comes back as 180 hours. And again, we look on the battery packet, and we find that that comes back as a standard deviation of those batteries should be 3 hours, okay? So let's let's go for a 95% confidence interval. And let's suppose it's symmetric, okay? So symmetric just simply means that the margin of error gets added and subtracted to our sample mean. In other words, we're looking at the same kind of area each side of our sample mean, okay? So let's first of all figure out, do we have to use a t-distribution or a z-distribution? Okay, so, well look, is n1 greater than or equal to 30? And is n2 greater than or equal to 30? That's the first question that we need to ask, okay? Second question we need to ask is, do we know sigma 1? And do we know sigma 2? In other words, do we know the population standard deviations for both? Okay, so let's ask those two questions. Okay, so if the answer to that question is yes, we ask that question. If the answer to that question is no, we use that question. If the answer to that question is yes, the answer to that question is no. Okay, so we use z distribution down here, t distribution here, t distribution here. Okay, so let's actually go ahead and ask that question. Well, look. Is n1 and n2 greater than or equal to 30? Well, n1 is greater than or equal to 30, fantastic. But n2 is not greater than or equal to 30, okay? So therefore, the answer to that question would be no, okay? So therefore, we use a t-distribution instead. If we went on and asked the other question, well, actually, we do know the population standard deviation for both. So even though we do know the population standard deviation for both, because n1 and n2 is not greater than or equal to 30, we have to use the t. So remember, if the answer to either of these questions is no, we use the t-distribution. Otherwise, we use the z-distribution. So let's actually figure out what is our degrees of freedom. So I write degrees of freedom down here. So remember, the degrees of freedom is just n1 plus n2 take away 2. It's just simply the degrees of freedom of each of these two types of batteries added together. So n1 is equal to 40, n2 is equal to 25, and I need to take away 2 from that. So okay, 40 plus 25 is 65, take away 2, that's going to give me 63 as my degrees of freedom. Okay, fantastic. So let's actually jump in and let's work out how we need to calculate our, our margin of error. So just remember, what we're doing here is we're calculating a difference in the means. So we need to find, first of all, the difference in the means. So x bar 1 take away x bar 2. So I want to find, well, okay, a confidence interval for the difference in the population means. Okay, so the difference in the population means of battery 1 and battery 2. So I want to find what's the confidence interval for the difference in the population durations, so the population mean duration of these two batteries. So in other words, this is going to be x1 bar, take away x bar 2, okay? Take away whatever our margin of error is, and then the upper one is going to be x bar 1, take away x bar 2, plus whatever our margin of error is, okay? So let's first of all, I'm just going to jump in and calculate what m is going to be. Well, okay, I'm using a t-distribution, okay? So I need to look up the number of standard deviations in our t-distribution. Our confidence level is 95%, okay? So it's 95%. So I need to work out how many standard deviations I'm looking at, okay? Then I need to multiply that by our standard error. So just remember our standard error, well look, the first distribution is going to be x bar 1 is going to be normally distributed with a mean of 200 and a variance of 5 squared over 40, because of course by the central limit theorem, okay? The distribution for battery 2 is going to be x bar 2, normally distributed. The mean is 180, the variance is 3 squared, and I'm going to divide that by a factor of n, so 25. Which means that our overall distribution, so in other words, x bar 1, take away x bar 2, because that's what I want, the confidence interval for a difference in the means, that's going to be normally distributed still. It's going to be the difference in the mean values, so in other words, 180 take away, 200 take away 180, because remember the order matters, it's x1 bar take away x2 bar. So the mean is going to be 20, but the variance, remember, is just basically adding these two variances to each other, okay? So it's going to be 5 squared over 40 plus 3 squared over 25, okay? Which means that our standard error, so remember our standard error is just going to be the square root of all this. So our standard error is just going to be 5 squared over 40 plus 3 squared over 25, all square rooted. That's our standard error. Okay, so that's what I need to multiply down here, okay? So I've got 5 squared over 40 plus 3 squared over 25, all square rooted, okay? It's basically the equivalent of standard deviation, because we don't call it standard deviation, we call it standard error, because it's literally looking at how far you are away. It's the central limit theorem, it's how far you are away from your expected mean value. Okay, but that's how we calculate it. So you come up with your normal distributions for each of these two batteries, simple as that, and you just simply combine them together like so. Okay, so let's have a look at this. Okay, so let's first of all find our 95% value. So what's our degrees of freedom again? Our degrees of freedom are 63. So let's bring up our tables. So we need to look at 63. Now you notice in the tables, the degrees of freedom, the closest you can find is 60. The reason being is because look at all these values. They're basically exactly the same. The reason being is because you're basically looking at a Z curve now, okay? So all I'm just going to do is select the closest value I can find in my tables, which in this case is 60. Okay, so this is 60 in this case. So let's block this out. There we go. Okay. Now, what confidence interval am I looking at? So I can use my, what was it, 95%, was it? Yeah, 95% confidence level. Of course, if I wanted to use the tail probabilities, well, I'm basically saying that the probability underneath there has got to be 95%, which means the probability up here and up here has got to be 2.5% each, because of course they've got to add together to make 5%. So I could look at my tail probabilities of 2.5%. In other words, that column there, okay? But just to make sure, I could also use my confidence level of 95% and just find the overlap. So either way, I'm looking at that column there, which is going to be 2 units of standard deviation each side of the sample mean. So let's come back up here. So I basically found T star is going to be 2. Okay, that's my number of standard deviations each side of the sample mean. I then to multiply that by the square root of all this lot. So I am going to bring my calculator up and see what that comes out as. Okay, so we have got, it's a big one, so 2 times by, I'm going to go square root, then underneath the square root I'm going to put my fraction. So fraction, and I'm going to go 5 squared over 40. Going to go to the right, okay, and need to add on another fraction. So you notice I'm still underneath the square root. Add on another fraction. I'm going to go 3 squared over 25. Hit equals, that's my margin of error. I'm going to give it as a decimal, so that's 1.98. That's my margin of error each side of my mean. Okay, cool. So in other words, my confidence interval for the difference in the means, so mu1 take away mu2, Well, it's going to be x bar 1 take away x bar 2. Well, we work that out as 20, right? It's 200 take away 180. And I'm going to take away 1.98, that's my margin of error. And my upper value, well, that's again difference in the sample means, that's 20, plus my 1.98, okay? So just a reminder, if you didn't quite follow that, the 20 is basically x bar 1 take away x bar 2, okay? Well, that's going to be 200 take away 180. I'm just using my values from above, okay? And that's the same thing down there. Okay, so it's the same thing. So let's have a look at this then. So, okay, my lower value is going to be 20 take away 1.98. That's going to give me 18.02. So that's my lower value. This is the lower kind of mean duration, okay, 18.02. And mu1 take away mu2 is going to be 21.98, okay? So in other words, what I'm saying there, the way to interpret this is slightly different. Because remember, this is not the mean durations anymore. This is not mean durations, okay? This is the difference in the mean durations, okay? So have a look at this, right? I'm basically saying that the difference in my mean durations is between 18 and 22, more or less, okay? I'm doing a bit of rounding there. But I'm basically saying the difference of these two batteries, the difference in the mean durations of these two batteries is between 18 hours and 22 hours. In other words, I'm saying that mu1 take away mu2 has got to be positive. It's got to be around the 20 mark. Okay, so because it's positive, then that means if I just do a little bit of rearranging, that mu1 has got to be greater than mu2. In other words, the mean duration of battery 1 has got to be greater than the mean duration of battery 2. In other words, I can be 95% confident that battery 1 will last longer than battery 2. Does that make sense? Okay, that's a really important point. So if you're looking at difference in the means, you're not just looking at average duration anymore, you're actually looking at the difference in the average duration. Is there a difference between the mean duration of these two batteries? So because the mean duration, so mu1 take away mu2, has to lie between 18 hours and 22 hours, well, that value is positive. Okay, it's about 18 to 20 hours, right? Difference is about 18 to 20 hours, but either way, that difference has got to be positive. So therefore, if I just rearrange that inequality by adding mu2 to both sides, then I get mu1 is greater than mu2. In other words, the mean duration of battery 1 is greater than the mean duration of battery 2. If I had a situation like this, so let's suppose another example, let's suppose that my batteries kind of came out as -5, less than or equal to mu1 take away mu2, less than or equal to, let's say, 3. Okay, that's my confidence interval. Let's just suppose that was my confidence interval. Okay, well, in that case, are you happy that mu1 take away mu2, it kind of spans 0, okay? So I can say that mu1 take away mu2 is approximately equal to 0, okay? Because it spans 0, because it goes from negative to positive. Have a look. Negative to positive. So therefore, because it spans 0, the difference in the two mean values is approximately 0, which means when I rearrange this, I get mu1 is equal to mu2. In other words, there's no real difference in the mean durations of my two batteries if my confidence interval spans 0. If I have another situation, let's say I have -43 less than or equal to mu1 take away mu2, less than or equal to 38. Okay, so let's suppose I had that as my confidence interval. Sorry, -38. Let's suppose I had that as my confidence interval instead. Well, what I'm basically saying there is that the difference in the mean durations is between -43 and -38 hours. So what that literally means is that mu1 take away mu2 has got to be negative. Either way round, it's got to be negative because I'm spanning two negative values, okay? So therefore, if I do a bit of rearranging in that case, I'm basically saying that mu1 has got to be less than mu2, okay? So you notice that the order of the operations really matters. In this case, I always look at my first group, take away my second group, and that will tell me, if it's positive, it will tell me that my first group has a mean duration that should be greater than my second group, okay? If I find that the mu1 take away mu2 in my confidence interval is negative, it means that my first group has a mean duration which is less than my second group at the 95% confidence interval. Whereas if it spans 0, it means that there's really no difference between my two groups, okay? So it's always done. So confidence intervals, you can actually tell whether there is a difference between two groups. You can give a confidence interval. You can say, okay, I'm 95% confident. So in this case, I'm 95% confident that the mean duration, the differences in the mean duration is about 18 to 22 hours. Okay, which basically means that mu1 should outlast battery 2. So the mean duration of battery 1 should be longer than battery 2. Whereas these situations down here, well, okay, if I have a mean duration between -5 and 3, means that the differences in my mean durations span 0, which means that there's really no difference in my mean durations. Whereas if I have a situation like this, basically saying that the differences in my mean durations is negative, then it means that the battery 1 should last less time than battery 2 on average, okay, at the 95% confidence level. So confidence levels are really, really powerful. They're a really simple idea. It's just simply saying, well, look, I want to basically consider this amount of my data. This is my sample data. I want to think, well, this is my spread of my distribution. I've got my distribution kind of drawn out. Basically say, well, look, I want to consider 95% of my data. Okay, well, if I'm considering 95% of my data, that basically means that I'm taking 95% of my data in there, and I basically form a confidence level to say, well, look, this is where, or confidence interval rather, this is where my true population mean should lie 95% of the time. Okay, so really, really powerful and important idea, but really simple idea.